All right, last episode for this unit is about drawing the structures into the appropriate shapes, the molecules into the appropriate shapes, in addition to looking at electronegativity again and how we can identify bonds through electronegativity, and then lastly looking at what are called intermolecular forces that help combine molecule to molecule, okay? So we have something called VSEPR. I know it doesn't even look like that, but that's how we pronounce that acronym, is VSEPR. And so we've drawn out a molecule. Sorry, let me take a step back. We've drawn out a molecule, but the way we drew it previously is not in the way that the molecule actually is shaped, based on the electrons wanting to be as far away as possible. And so we have what's called this valence shell electron pair repulsion model, or VSEPR, which teaches us basically why do the electrons do what they do, okay? And this model also shows how the compounds come into contact with each other to react, okay? Basically helping us understand why we would have, I mean, this is getting much deeper into chemistry than we really need to go, but like the orientation of the molecules when they run into each other, et cetera, et cetera. Instead of everything just being nice straight lines, we have things that are bent at particular angles, et cetera, okay? So this model illustrates how the shared and unshared bonded electrons will repel each other, and this is in order to make sure the electrons have minimum repulsion to each other around that central atom. Because again, they're electrons, they're negatively charged, they want to repel, they want to be put away. So this puts the atoms into, and the bonded atoms, they will create particular shapes based on the angles that these electrons will push each other, okay? And that's what I'm showing over on the side here. I mean, it's a little bit tough to see. This is basically all the different shapes that are possible out there. We're not going over all these, that's a lot. We're only going to go over about 5 different shapes, but there's lots and lots of things that the atoms can do to make sure that all of the electrons are as far apart from each other as possible, okay? And it turns out this is largely due to the unshared pairs of electrons wanting to have more space because they just when they are alone, when you have these lone pairs, they occupy a larger, what is called orbital area than a bonding pair, okay? Those electrons, when they're bonded between two atoms, they can kind of squeeze together a little bit more while they're in between those two atoms themselves, okay? So what are these different shapes, okay? The first one is the linear shape, okay? That means the angle, the bond angle for a linear shape is 180 degrees, because that's what a straight line is. This is generally created when you have two atoms bond. When two atoms are bonded together, they're going to create a linear shape, because one's on one side, one's on the other, regardless of what the rest of the electrons do, all right? That's going to be the best shape for two atoms. When there's 3 atoms, this shape will be created if there's no lone pairs on the central atom, okay? And that's because those lone pairs are what's going to start pushing the bonds away. When there's a double or triple bond, this is always linear between those two atoms. Between those two atoms, that will always create a linear bond between those two atoms. That's just because when you form more than one bond, I mean, I'll kind of draw it out here a little bit. When there's 2 bonds in between them now, okay, and let's say there might be something else over here. When there's 2 bonds in between, these don't bend well together. They want to stay very rigid, very straight. When there's a triple bond, it's even worse, okay? They're not going to bend. If it's just a single bond, that's a little bit more malleable, pliable, whatever you want to use for it, that you can bend it, okay? So linear, 2 atoms, 3 atoms with no lone pairs, or double or triple bonds. The second shape that we will run into is bent, all right? And so this is our example of like a water molecule, all right? And so what happens here is this is created when there's 3 atoms bonded, but there are 2 bonding pairs and 2 lone pairs on the middle atom. In other words, there's 2 bonds and 2 lone pairs. The good example here is water. So I mean, we could draw water out like this when we draw our Lewis structure. But what actually happens is, for the maximum amount of space we can have, instead of leaving the molecule like this, that one lone pair on the bottom moves to the top, and what those lone pairs will do is then they basically push the bonded pairs on down. All right? They push them on down and away. They bend them away so that basically these lone pairs have all of this space now at the top, and the shared pairs do not need as much space. So the angle that's created here is 104.5 degrees. 104.5 degrees. It actually, I mean, it's crazy how this all kind of has developed. It's just nature finding the best particular shape to be in to come to the lowest energy possible. One hint I can give you with this is usually formed when you have O group atoms in the middle. Okay, so oxygen, sulfur, selenium. If it's just those atoms and then it's two single bonds, we're going to form a bent molecule. Next shape, trigonal planar. Trigonal planar, okay, is created when you have 4 atoms and you have 3 bonding pairs and no lone pairs. Okay, this one is fairly rare. You're not going to run into this one too much. You might have a polyatomic ion that does it. The only one that I can think of that really does it in some cases is boron will do it, okay? Because boron, I know it's right next to basically being a metal, but it's kind of at that borderline being a metalloid, all right? It will have no lone pair, so it doesn't have to push, and we can put all of those bonded atoms as far away as possible, okay? So that's one that's a little bit strange, and you're also probably going, wait a minute, how does that work if it only has 6 electrons on it? It's one of those kind of weird things, okay, that basically happens with it, okay? Trigonal pyramidal, this one's more common, okay? So what happens here is I know people get these two confused. The trigonal pyramidal is much more common, okay? For trigonal pyramidal, this is created when, again, you have 4 bonded atoms, 3 bonding pairs, and 1 lone pair. So this is going to be primarily created by the N group atoms, and you can see what we got here. Essentially, this might show it a little bit better. Like we might draw out NH3 ammonia like this, but the idea is this lone pair will push both of these shared pairs down a little bit, and so it'll create this 3-dimensional, unfortunately I'm on a 2-dimensional platform, okay? But the idea is those form a pyramid triangular shape underneath of it, and that angle is 107 degrees from each other, okay? So a little bit farther away than what we had before, okay? So that's where we can create that shape, trigonal pyramidal. Again, much more common than trigonal planar. Then we have tetrahedral, very common one, 109.5 degree angle. You do actually have to remember these angles in terms of knowing where they are formed from and why. Okay. This is created when you have 5 atoms bonded and you have 4 bonding pairs with no lone pairs in the middle. This is done by the C group, by carbon, by silicon. Okay. And again, it's one of those things of, instead of where they all just go straight around each other, this is actually called a square planar shape. We're not doing square planar shapes. It turns out where, again, it's like the pyramid, and this is where you have to think of the 3 dimensions with it. It's where like this one will press out of the board, and then these two will kind of create the pyramid underneath on both sides, and then again, this one's kind of going into the board, all right? But creating essentially the trigonal pyramidal shape with an atom on top. That's what tetrahedral is. So created by carbon atoms. So again, one of the things you'll do is you'll draw out the structure, and if you use kind of these ideas of what's involved, do we see a lone pair? Lone pairs will cause this bending to occur, all right? If it's a tetrahedral, we kind of know it's going to just form all 4 of these atoms all around it, okay? And again, let me show you that again, how to draw that. When I say please draw it on your paper or whatever, we would draw it like this, where you could just draw one up and then you draw 3 like a pyramid underneath, okay? And that would be the tetrahedral shape on that one, okay? All right, so as I was saying, what I was showing there was what's called molecular geometry. I'm sorry, let's say this again, okay? We have what's called electronic versus molecular geometry. Electronic geometry is what we were doing with our Lewis structures, where if we just draw everything perfectly kind of straight and box-like, is the way I'd like to say it, okay? This is the shape that we have before I have the lone pairs all starting to repel. So it's very, 2-dimensional, essentially, is the electronic geometry, okay? The molecular geometry is where we get to VSEPR, and where we actually create the correct shape. So you can see my example here, and this is one we already just did. H2O, its electronic geometry would be a linear molecule, because I would just draw the O's on both sides, the O and then the H's on both sides, the molecular geometry would be bent. So there is a difference between those two that we might ask and go, what's the electronic geometry, what's the molecular geometry? Okay? Mainly with bent. That would be linear versus bent, and trigonal planar versus trigonal pyramidal. Okay, we're not doing square planar. It would be square planar versus tetrahedral, but we're not doing that. So here we go. So what I get here is, again, basically what would it give me the electronic and molecular geometry. And again, they could possibly be the same. For N2, we learned that one should have been a triple bond. This would be linear for both electronic and molecular. That triple bond, it does not bend, so that's a linear shape. And it's only 2 atoms. For carbon tetrachloride, this is one I would not ask about the electronic geometry because, like I've said, we're not doing square planar. But this would be the electronic geometry. But then the molecular geometry, so many dots. I might leave the dots off just to speed up. We'd have it like that, where we'd actually bend those atoms down a little bit. Okay, bend it down. All right. NBR, this is one that I could ask about both shapes. NBR, the electronic geometry would look something like this. So that would be considered a trigonal planar shape, essentially. Okay. I know we could bend the atoms up and everything like that. But then the molecular geometry would be like this. BR, 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 and would be the trigonal pyramidal shape. Okay. BH3, we're just going to go straight to molecular. That would be H, H, H. It doesn't actually have any lone pairs. It turns out that this is actually okay. And we have that formula, boron trihydride. Boron is, again, one of those weird ones that just works out. Okay. So that would be this would be trigonal planar. Okay. Trigonal planar. All right. CO2. CO2, we got O on that side, O on this side. So this would be linear electronic and linear molecular. SEF2, this is probably, again, the most common one that we would play around with, where SEF, F on both sides. Linear electronic, but then it would be bent molecular. Okay, so that's what we're looking at. You're going to have to be able to possibly draw both. Primarily the molecular is what we're looking at. So, moving to the next thing. Bond character. Okay, we have what are called ionic bonds. We've already talked about these. Okay, bonds between a charged metal and a nonmetal. This is the strongest of bonds that we have out there. An ionic bond is created by that electrostatic force. It is very, very strong. What we then have is what are called polar covalent and nonpolar covalent. And I'm bringing them both up at the same time. Okay? Polar covalent is a bond between unlike nonmetals. All right? So, again, it would be like F and O. Okay? I mean, it just makes sense. Obviously, 2 different nonmetals. Okay? This type of compound is asymmetric, which means it is not the same everywhere. Okay, it doesn't create the same, it doesn't have a mirror image when you cut it vertically or horizontally across the compounds. Okay, it's not the same on all sides, essentially. These are created when the elements have different electronegativities. Okay, when there's different electronegativities. And then atoms do not share those electrons evenly. So that's what happens afterwards. If they don't have an equal electronegativity, one atom is able to pull those electrons a little bit more than the others, and basically those electrons spend a little bit more time on one atom versus the other. This then creates what's called a partial charge on the molecule. And again, I'll draw this out in a moment. It'll create a partial charge on the molecule. We call that a dipole. I guess I'll draw it right now. So water is a perfect example. Is our most common polar molecule, polar covalent molecule. Okay? So that is this is also why we get into molecular shape, because we can see that it's asymmetric. So water is asymmetric, it's polar. O has a higher electronegativity than H. What that means is these electrons that are being shared actually spend a little bit more time with the oxygen, and we draw that as a little delta symbol, a lowercase delta. It looks like that. And basically this side of the molecule takes on a partial negative charge. It's not a full -1 charge, but a partial -1 charge. All right? And the other side creates a partial positive charge. And so when that happens, that creates new properties for this molecule, and the way that it will bond with each other and with other objects and how it will react. That will cause some serious consequences, essentially. It also has to do with whether objects will dissolve. So there's a lot of importance with whether it's polar or non-polar. Okay? So that's what we're talking about by dipoles and creating a polar molecule. A non-polar covalent is a bond between like nonmetals, in other words, two of the same. The compound is symmetric. There is a way to make it without, you can create non-polar covalent compounds with different atoms if the whole compound is symmetric, all right? And basically that means you have a tug of war from the same type of atoms on the opposite sides of a different atom. The atoms will be shared evenly amongst the whole structure. This will not create any dipoles. So non-polar, as its name implies, means no poles. Polar means positive and negative poles. So these are the three possible what we call bond characters, where I give you a molecule now, we determine if it's ionic or covalent. If it's covalent, is it polar or non-polar? Ionic is basically the extreme perfect polar formula. I don't want to call it molecule because, again, we don't really call them molecules, but the idea that you clearly have two opposite charges. Okay. So how can I predict based on shape? How can I predict polarity based on the shape of the object? If it's symmetric, that means it's non-polar. That means it's same on all sides. Okay? In other words, you can cut the molecule in half vertically and horizontally, and it's the same on both sides of it, a mirror image. Only linear, trigonal planar, and tetrahedral shapes can be symmetric. Okay? Asymmetric means it's going to be polar, not the same on all sides. Not a mirror image on each side, again, horizontally and vertically. You could possibly have it the same vertically, but then if you cut it horizontally, and it's asymmetric, it's polar. So it has to be able to do it both. Okay? All shapes can be asymmetric, but bent and trigonal pyramidal are always asymmetric. So here's your water molecule. So what we're saying is this symmetric or not? If I cut it this way, that is symmetric, but if I cut it across the middle here, now that's not symmetric from the top and bottom. So this would be a polar molecule. We also know that it's bent, and therefore it has to be polar. Okay, that's kind of the other clue. So if you know your shapes well, you can figure these out a little faster. Okay, NH3, same thing. There are ways that we could try to cut this where technically I could cut this, and it's kind of tough to see, through the middle, where basically I cut right along this one, and it's the same on both sides, but then if I cut through the middle, the horizontally across the nitrogen atom, it's not the same side, top and bottom of it. Again, that's trigonal pyramidal, so that would be polar as well. Okay? Non-polar would be like CO2. I do have two different atoms, two different nonmetals, but the idea here is I cut it through the middle, it's symmetric on both sides. If I cut it through the middle horizontally, it's the same on both sides. All right? And the idea is, while these oxygens will pull the electrons more, they pull equally on both sides, so the electrons stay where they are. Okay? They're able to stay exactly where they are. So that would be nonpolar. This one right here, a tetrahedral. With tetrahedrals, what you do is go, are you the same on all sides? If you answer yes, it's nonpolar. If you answer no, it's polar. One of the rules I sometimes use with it is you can't have two no's, okay? You cannot have two no's. You can be symmetric and nonpolar, asymmetric, not symmetric, and polar. You cannot have two no's. If you say it's not symmetric, it cannot be nonpolar, okay? It is not nonpolar, all right? I know it's kind of tough because all those nots. So if this was a Cl on top, then this would be a nonpolar molecule. All right, and we should get some practice in class actually making these where you can kind of tell that hands-on making those models, that it's all symmetric everywhere. Okay. Another way to figure out bond character is we can use the electronegativity of each of the atoms. And so this would have to be given to you in a problem. What you would do is you just simply subtract the two electronegativities of the two atoms I give you, and then you basically compare, you look at the answer and you compare it with a particular chart like this one. If you subtract the two and you're greater than 1.7 of electronegativity, it's mostly an ionic compound. It's probably you picked a metal and a non-metal, and they're very different, okay? And again, this goes back to the electronegativity trend where as we go across, we increase electronegativity. I know there's some variations to it, but that's basically what we're looking at. If we subtract two elements and it's between 0.4 and 1.7, it's polar covalent. Less than 0.4, it's still covalent. It's mostly covalent. What we mean is it's still polar, but you're not going to find that dipole, the positive and negative charge, as effectively. Okay, and then clearly, if it comes out to 0, that means you have two of the same atoms, and therefore you're creating a non-polar covalent bond. Okay, so even going back, just so you since I'm thinking about it. With that example, like if I say Cl, 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 each of these individual bonds is a polar bond. But the thing is, these two polar bonds are working opposite each other, again, are creating that pool. These two are creating that opposite pool. And so what happens is they all cancel each other out. So again, you're never going to be asked to combine multiple atoms. This is only, hey, you have lithium and phosphorus. What type of bond is formed? Subtract the two, okay, and so forth. You might get some interesting answers again with it. Again, the idea is ionics are generally with metals and a non-metal, so there are some weird things that can happen out there, and that's where we have a lot of exceptions, and we'll try to push through those as we need to. All right, so sorry, there's some examples. K and Cl, if you subtract those two, 2.34, it's ionic. O and S, it's going to be 0.86 polar covalent. Again, I'm just subtracting the two numbers, 3.44 minus 2.58. All right, and then N is 0, and then B and H would be 0.06. So that's where, again, it's kind of weird where that forms just a pretty much almost non-polar covalent molecule, but it's still a little bit polar. Okay. So, getting to like the last part here, intramolecular versus intermolecular forces. Okay, so kind of reviewing our bonds. We have been talking about intramolecular forces so far. Intra means inside, okay? Inside the molecule forces. So this is the force that is holding atom to atom together inside a single molecule. And you can see my chart there saying ionic, covalent, and metallic. We've reviewed those. These are all intramolecular bonds, intramolecular forces, ionic, covalent, metallic, okay? That is different from what we're getting to called intermolecular forces. And intermolecular forces is where you already have your molecule, but it will be attracted to another molecule. So this is between compound and compound. These are much weaker than intramolecular because, again, those atoms are really close together when they're in a compound. They are farther apart compound to compound. All right, so they are much weaker than the intramolecular force. There are three types of properties out there. We have what are called London dispersion forces, dipole-dipole, and hydrogen bonding. And what we're going to be interested in is how strong are these and when do they form? That's what I'm looking for. So when are they forming and how strong are these? Why is this all in the end important? It affects so many of the physical properties of the compound. All right, it'll affect what state of matter it is, it'll affect its boiling point, its solubility, its surface tension, its capillary action. Capillary action is basically how easily it's able to kind of build up along the side of walls. And then viscosity is basically its flow rate. What I need you guys to basically understand is, as I increase the intermolecular force between the objects, as there's a higher intermolecular force, which I'm going to start writing as IMF, is the abbreviation for intermolecular force. You will usually find these be solids. You'll have a higher boiling point. You'll have a higher surface tension. You'll have a higher capillary action. You'll have a higher viscosity. And you'll have a higher solubility in water, is what you're looking at there. So the nice thing is everything is increasing due to the intermolecular forces. All of these properties will be larger and will have more solid particles, solid states of matter. Because again, the idea if they're stronger, they're more fixed in place and they're going to create a more rigid structure. Okay? So that's what you need to know there. So what is London dispersion forces? Okay? London dispersion forces. London dispersion forces, I'm going to start with this one, is the weakest of the IMF, of the intermolecular forces. All right? This is created when I have a nonpolar compound. Okay? This is formed with nonpolar molecules. All right? And the idea is, as the name implies, there shouldn't be any charge. But what will happen is occasionally, and like it says, temporary instantaneous dipole, is there's points where, again, those electrons are moving so fast, for a millisecond, a microsecond, a nanosecond, that molecule might have a negative charge on one side just because it has an extra electron on one side before it moves back to where it was. And so this is called London dispersion forces. This is the weakest of all the IMFs, formed by nonpolar molecules. So if it's nonpolar, it's London dispersion. Okay, and that's the only one for nonpolar, so that's the nice thing. And it just allows these different nonpolar particles to at least come together, like a liquid, like oils and stuff like that. Oils are generally nonpolar, and the thing is, though, those oil particles are still attracted to each other some, just not super, super well. Okay, is what we're looking at. Going back to the viscosity part, this is where you have these particles that flow really, really easily, possibly. Okay, because they don't necessarily even need to stick together too much. All right, so this is kind of a bit of a blurry picture of it, but this is just showing where you have a helium atom and a helium atom, and for a brief moment when those two atoms come together, the electrons, just the way they're oriented, might cause them to attract a little bit, create a little bit of attraction where there's a little bit of a positive charge right here for a moment, and you can see the extra electrons here, slight negative, but then soon afterwards it'll go away. Okay, so I mean, this is how we have air particles basically also find that they're sometimes attracted to each other. Okay, dipole. These are stronger than London dispersion, so dipole is stronger. This is created when you do have polar molecules. So this is created by polars. Okay, so we do have to actually have the dipole created. Dipole means two poles. All right, so we actually are creating that partial positive and partial negative. Really what this thing is different, because we're going to see another one in a moment, this is created when there's no hydrogen. When no hydrogen, for the most part. Now there's exceptions to that. There can be ones with hydrogen that we still call dipoles. But basically when there's no hydrogen, I'm going to just mention that, it's a dipole polar molecule. Okay, and that's a little bit stronger between the two. So again, you can read through this carefully yourself, but it's the idea that it's created by a polar molecule when there's no hydrogens. But there's going to be exceptions in a moment. Okay, stronger though than London dispersion. Okay, so again, that's what this is trying to show. This is showing you some molecules, probably all the same type of molecule, but maybe that they don't have, like I'm going to just say, let's say for instance it's SCl2. Okay, a bunch of SCl2s. All these are SCl2s. SCl2 is a polar molecule, has no hydrogen, but it'll create these dipoles, these poles, and that'll attract the different objects together, different molecules together. Okay. The last one is hydrogen bonding. And as it says, this is a special type of dipole-dipole attraction. This is where I said there's exceptions. It involves hydrogen, but it only involves hydrogen when it's nitrogen, oxygen, and fluorine. So if you remember the acronym NOF, okay? Hydrogen bonds form when it's NOF. Basically, when hydrogen is with one of these three, and it's a polar molecule, we get what's called hydrogen bonding. And this is the strongest of all the intermolecular forces. This is why water has a very high surface tension. This is why water has a pretty high boiling point of 100 degrees Celsius. Okay? It's not solid, sure, but it's obviously it's in a liquid form, which is stronger than a gaseous form. Okay? So that's what we're looking at here. All right? Hydrogen bonds are the strongest of all of them. And it's only formed when there's hydrogen, but it has to be with nitrogen, oxygen, and fluorine. So I know it's annoying if we do H2S, okay? This is not going to form H bonds. We'd actually say this is created with a dipole. Like the intermolecular force is a dipole because it's not NOF. Now if it's H2O, now we call this H bonding. So annoying, but that's the way it goes. All right? So there you go. That's an example where basically these are like partial negative charges, partial positive charges, negative, positive, and that's why all the waters want to stay together. Okay. So this is what you're kind of left with, all right? It's kind of a good chart of figuring this out. And it also shows you the increased strength. So London dispersion forces are the weakest. Dipole's next, then hydrogen bonding. Ion dipole, don't worry about that. Ion dipole, ionic bonding, I'm just putting that all under ion, basically, okay? So what do we have? Are ions present? If you say yes, basically we're zooming straight off to ionic bonding, okay? Basically that's what we'd say. I'm not worried about are polar molecules present. That gets into basically when you create solutions and you put like salt and water, that would be an ion dipole force. So that's what that's saying there, okay? My thing would be, do you have ions? Yes, it's ionic bondings, okay? The bigger thing though will be more on the other side. There are no ions present, so your next question is it polar? If you say no, you got London dispersion, done. If it's polar, you have to go, do I have H, and is it bonded to N, O, or F? If yes, it's hydrogen bonding. If no, it's dipole. So you even see that with HBr right here, or CH3F. That would be dipole bonding. Okay? And this is just another kind of show with it. Okay? Another description showing the different things. So again, the intramolecular forces of ionic versus covalent, and then moving to intermolecular forces. And I believe that's it. So it's time to really, really practice. All right. Thank you.